Hi everyone, hope you're all doing well and staying safe. My name is Tayeh, and today I'll be presenting my paper, Distance-Based Anomaly Detection for Industrial Services Using Triplet Networks, authored by me, Sulaiman Aburakhia, Ryan Myers, and Dr. Abdallah Shami. We're all based in the ECE department at Western University in London, Canada, except Ryan, who's part of the National Research Council Canada. So I'll start off by introducing what is anomaly detection. It's the process of identifying unexpected items or events or observations in data sets which differ from the norm or from the majority of the data, and it's in various domains such as statistics, signal processing, and manufacturing, and it's also called outlier detection. Surface quality inspection is an essential part of the production process in all manufacturing industries around the globe for detecting anomalies. Predicting anomalies on time can decrease over-scheduled repair by up to 12%, maintenance cost by up to 30%, and the number of breakdowns by up to 70%. So as a result, and to keep up with the throughput demand while trying to realize a near-perfect quality inspection, machine-based visual inspections have been utilized in recent years instead of human experts to identify defective products, and in particular, convolutional neural networks. A convolutional neural network, or CNN, is a class of deep learning neural networks models that is most commonly applied to analyzing visual imagery. Its effectiveness comes from the fact that CNNs are fully connected feed-forward neural networks that uses convolution in place of general matrix multiplication in at least one of their layers, and reduce the number of parameters very efficiently without losing out on the quality of models, learning new higher dimensionality features with every layer. A basic requirement for training the CNNs efficiently on a classification objective is the accessibility of an adequately large amount of training data for each class. However, with well-optimized processes, there is often an abundance of non-defective samples and a relatively small amount of defective samples. To address this data imbalance challenge, the training objective can be shifted from defect classification to anomaly detection, ideally eliminating the need for any defective samples for training. So, can we actually achieve anomaly detection with no defective training samples? So some previous approaches in the literature, they still use defective samples for training or involve detecting anomalies in certain regions of an image, not capturing potential defects across the entire image. Other approaches involve training the CNN features based on solving a classification task rather than an anomaly detection task, and some involve utilizing computationally expensive image reconstruction sparse representations to identify anomalies. So lower image resolutions are used, which in turn lowers the accuracy of the anomaly detection task. So here comes our approach. Efficient CNNs based on residual networks are trained to explicitly learn a similarity metric for defective and non-defective patches of surface textures through the use of triplet network model. The defective samples used in the triplet network are artificially synthesized exclusively from non-defective samples via random erasing. The network is trained without any defective images on an anomaly detection objective due to the limited number of defective samples to train the network efficiently on a classification objective and to further generalize the solution to the surface inspection task. After training, a simple prototype pixel-wise subtraction method is performed between the evaluated surface and the prototype measurement for that particular texture surface in the feature space learned by the CNN, producing an array of distance values. A support vector machine, SVM, with a linear kernel is then applied against the mean and maximum distance values collected with the intention to maximize the separation between the defective and non-defective evaluated samples. The anomaly detection for known classes that are part of the training data set, as well as novel classes that are not part of the training data set, are explored for the industrial services. And in addition, the different defect types present in the testing batch are explored individually. The work presented in this paper further extends the methodology and results of Benjamin Starr et al. Work in anomaly detection with convolutional neural networks for industrial surface inspection, published in Presidia SERP 2019. But our work instead trains and tests on a real-world data set with a focus on industrial surfaces rather than artificially generated general texture data set. So the main contribution of this paper include artificially synthesized defective images exclusively from non-defective samples using lightweight random erasing techniques that do not require any extra memory consumption or parameter learning rather than using Gaussian noise. Implementing a deep residual-based CNN architecture with very small convolution kernels rather than large kernels. This allows the network to learn more interesting features while having a small number of trainable parameters. Maximize the margin of separation between the defective and non-defective images during evaluation by utilizing a hard margin SVM against both the mean and maximum feature distance values collected rather than varying threshold values against the maximum distance values only. and analyze the individual defect types to gain a deeper insight into the anomaly's perceptibility when using the proposed approach. The dataset used in this work is the MVTIC anomaly detection dataset. It's a modern comprehensive real-world dataset with over 5,000 images. It has 15 different industrial object and texture category classes, and each class has non-defective images and a range of defective images such as bent, broken, and cracked surfaces. 11 classes used in training and testing are for known class or explorations, and 4 classes are only used in testing for novel class exploration. Now we jump into the methodology. So the triplet network model is utilized in this paper for training. This architecture allows an input of 3 different images to be fed into the same CNN, where the weights are shared. Where the weights are shared. The first image is called the anchor A image. The second image is called the positive P image, and the third image is called the negative N image. The A and P images belong to the same class, and the N image belong to a different class. Features of each image are computed after passing through the CNN before calculating the Euclidean distance between the resulted features of A and P, and the Euclidean distance between the resulted features of A and N. This allows the network to directly learn a similarity metric via defect metric learning, which is beneficial as the number of object classes is not specified and could be boundless. Afterwards, the resulting D1 and D2 scores are inserted into a row vector, then placed into the softmax function, yielding an output vector whose sum is equal to 1. The output vector is trained with the target vector 1, 0 for each triplet vector of APN, ensuring the network assigns a higher similarity score between images A and P and a lower similarity score between images A and N. Before training the network, all training images are resized to 1024 by 1024 pixel resolutions, converted to grayscale and normalized via min-max scaling to rescale their values between 0 and 1. The CNN here is only required to learn similarities between patches of 64 by 64 pixels, and that idea is inspired by previous work, which demonstrated that data is sufficient for defect classification, and in addition, it increases the amount of training data available. Defective images used as the N image input into the network are instead artificially synthesized exclusively from the non-defective images using random erasing. The random erasing technique utilized essentially erases a random part of an image of a random size, enhancing the sensibility to local deviations. So the figure at the bottom visualizes an input sample of APN to the triplet network, and as you can see, the negative image is where it has the random erasing applied to it. The CNN implemented in this paper is based on deep residual learning and uses very small convolutional kernels inspired by the work of the widely known VGG16 network. So ResNets eased the training and optimization of networks by enabling layers to learn a residual function reference to the input layer as opposed to learning unreferenced functions. And the VGG16 network demonstrates how a deeper network with very small convolutional kernels of 3 by 3 produce more accurate results compared to the previous configurations on the ILSV Challenge 2014, as well as reduce the number of parameters in the network. So the first 3 layers in the network presented this work consist of 2D convolutional layers with rectified linear units, ReLU, activation functions, and kernel sizes of 3 by 3 to learn interesting features, followed by a 2D max pool layer with a window size of 2 by 2 and strides 2 by 2, which acts as a downsampling filter. Afterwards, 7 residual blocks are stacked next to each other. The figure at the bottom visualizes a block where each consists of 2 consecutive 2D convolutional layers with ReLU activation functions and kernel sizes of 3 by 3 applied on the input, which produce an output spatial resolution that is reduced by 4. Their output is then added to the output of a 2D cropping layer, which applies a spatial dimension crop of size 2 by 2 to the height and 2 by 2 to the width of the input. The entire network is built convolutional to allow the weights to be shared between the training and testing models. All networks are built and implemented in Python 3.7.4 and using the open source TensorFlow and Keras MLDL libraries. As for the training network hyperparameters, the Atom optimizer is utilized with a fixed learning rate of 0.0001 and a batch size of 256 samples. The mean absolute error loss function is utilized and the network is used for 40 epochs. These values were selected based on iterative parameter tuning experiments. As for defect detection evaluation, a class prototype is first created by embedding a large amount of non-defective data of that class into the CNN to obtain a set of features. Afterwards, the testing images are embedded into the same CNN and the Euclidean distances between the prototype and the testing images features are calculated. The resulted maximum and mean distances are then subjected to an SVM with a linear kernel with the intention of maximizing the separation between the defective test images and the non-defective test images. An SVM with a linear kernel allows the robust classification algorithm to be fast and memory efficient, as it's just a single inner product with OD prediction complexity, where D is the number of input dimensions. The regularization parameter C is kept constant at 1 exponent 8 for a harder margin SVM that imposes a larger penalty for wrongly classified examples. So to evaluate how well the proposed approach discriminates between the defective and non-defective images for each surface and the individual defect types, the area under the curve of the receiver operating characteristic is calculated. The higher the AUC, the better the model is at predicting true positives and negatives. Experiments are all repeated 3 times and the average AUC score is recorded. As the work presented in this paper extends the approach used by Starr et al., their approach is tested against the MVTIC AD for a comparison of results. The figures 6 and 7 show the individual and mean AUC scores for Starr et al. Approach and the proposed approach, respectively. The classes are the blue column headings at the top, and the defect types are the blue row headings to the left, where the first part are known classes and the second part are novel classes, i.e. they're not used in training. Upon examining the table of results, whatever cell you want to look into, the proposed approach produces a better score for the majority of the individual class defect types and a better mean score for every single class and defect type. If we look at the green cell, the proposed approach scores an average class mean of 0.093 higher and average defect type mean score of 0.097 higher. Furthermore, it can be observed from the class mean scores that the proposed approach achieves some state-of-art results for both known classes and novel classes. In total, only 3 classes achieved a mean score less than 0.9, 4 scored between 0.9 and 0.95, and the remaining 8 scored between 0.95 and 1. In particular, 3 classes achieved a perfect score of 1, where only 1 class was known and 2 were novel, further demonstrating how well the method translates to unknown inputs. In regards for the defect types, it can be seen from their mean score that the proposed approach achieves some state-of-the-art results. Out of the 20 different defect types, only imprint and scratch defect types achieved a mean score less than 0.9. 15 defect types achieved a mean score between 0.95 and 1. The figures show 2 scatter plot examples with perfect linear SVM separation between the defective and non-defective samples. The plot at the left for a hazelnut class with imprint defects shows a separation mainly via features, max distance with a prototype. And the plot at the right for a transistor class with misplaced defects shows a separation mainly via features, mean distance with a prototype. As for the conclusion, this paper demonstrated how deep metric learning can be effectively used for surface anomaly detection of different defect types without the use of any defective samples. It further showed how this approach translated well to novel classes that were not part of the training dataset, as 2 of the 4 novel classes achieved a perfect AUC score of discrimination between the defective and non-defective images. Results were promising, but they could still be improved for certain classes and defect types. Future work include exploring additional texture and object training datasets, as that can allow the network to learn more powerful and complex features, as well as exploring other CNN architectures implementations and further optimizing the network hyperparameters for better network performance. As an acknowledgement, this work is partially supported by the National Research Council of the Government of Canada under Project AM1051. Thank you all for listening, and I can take any questions that you guys have now.